Hello, good afternoon to all. We are continuing our series of plenary talks, and this afternoon we have the pleasure to have with us Professora Cecília Salgado from the University of Rio de Janeiro. Cecília earned her PhD at Paris 7 under the supervision of Hindri. She held postdoc positions at the following prestigious Hausdorff Institute and the Max Planck Institute in Germany, and also the University of Leiden in Holland. And she was also the recipient of the 2015 L'Oréal Prize for Women in Science. And today's talk, the title is Arithmetic and Geometry of Algebraic Surface, the place of elliptic, fibrations, and K3 surface. Thank you again, Cecília, for accepting our invitation. Thank you again.
Thank you very much, Amar, for the invitation, for the introduction. Jaqueline Matofua, who also wrote to me inviting. So it's a great pleasure to be here with you. And I think we can get to it. Let's share the slides. And okay. Now you can see my slides, and I will try to go in a slow pace, but I want to have something for the whole public. So I want to start with the basics, then I will reach some part where will be the core, where I still hope to reach most of you. And in the very end, I want to give you a little bit of research of what has been done in the last few years and treat one special problem, okay? So as I said, with the plan, we are going to start by giving you a flavor of what this field is doing. So what do we care for? And this is the first slides. Then I will tell you a little bit about curves. So, what's known about geometry of curves, also the number theory related to them. Then I will pass to the core of the talk. As I said, I will deal with surfaces, and I will slowly present the geometry of surfaces, and we will really first present the classification of them, and to then move to problems of number theory. So we are going to be really wondering of what happens to solutions over the rational numbers, or over Z, the ring of the whole numbers. Then finally, in the last part of the talk, I would like to present a tool that it's very useful to tackle problems both in 3 and 4 of this slide here. And the goal for me here would be to maybe use curves to get to know a little more about surfaces. That's the thing I want you to bring home today from this talk. So what I want to stay is that when we reach something that we want to study and we lack maybe really, let's say, when we don't have information about them in a broad sense, one way to do it is to look in a smaller sense. So it's to look for things that we know about. And that's what this talk is going to be about. So it's using curves to get to know surfaces. That's what I want you to bring home from here. And finally, the last part of the talk, I will spend some time speaking about a very special class of surfaces, namely K3 surfaces. And my choice for this class has to do with the fact that they are, you can really find them, in many fields of mathematics, not only in geometry and in number theory. But I will have one slide summarizing this fact, and then we get to relate the two that I will describe in part 5, the fibrations, with the K3 surfaces. So let's start, finally. So what the field is all about, arithmetic and algebraic geometry. So algebraic geometry is concerned with the sets of solutions of systems of polynomial equations. So the simplest kind that you might want to study, right? And usually over an algebraically closed field, such as the complex numbers, okay? And these systems of polynomial equations, they correspond to what we call varieties. So I'm going to call varieties for short. And When we pass to arithmetic geometry, or more precisely, Diophantine geometry, we care for the same systems of polynomial equations, but now we are concerned with solutions over a more general field, maybe. So maybe the field of rational numbers, or a finite field, or even rings. So we are really caring more generally, or more specifically, if you want, well, two sides, for solutions over different kinds of fields and even rings. So that's what we are concerned with. So this talk is going to be about polynomials and the solutions that lie either in the whole numbers or in the rational numbers. So let's introduce a notation before we go on that will remain in force for the rest of this talk. And that's the following. So the notation is usually the letter X, big X, is going to be reserved to talk about varieties. So there can be curves, surfaces, that will always be denoted by big X. And X of K, so with these brackets, okay, it's going to denote the set of solutions for these polynomials that lie in the field K. So if my variety, I mean, I'm going to show you a few of this polynomial soon, and it's going to be clear what I mean by that. And many times, instead of talking about solutions, I'm going to be speaking about points that lie in K. So I'm going to be speaking about K points. And if you're new to the subject, or just if you don't want to think very hard for this talk, we can assume, and still we get a lot of nice results from it, that the field K is the field of rational numbers, okay? So that's a deal for today. So before I go on and talk to you about more general facts, I want to have a look at a specific but very celebrated problem, namely Fermat's last theorem, which I assume you're all familiar with, but still I will state it here for you. So this was shown in 94, 95 by Taylor and Wiles. And what the theorem tells us, it's really concerned, as we spoke in the previous slide, with polynomials. So here we have a polynomial equation, namely x to the n plus y to the n equals to z to the n. So in 3 variables, okay? And what the theorem says is not that this polynomial has no solution, but something harder. It actually has solutions, right? So plug x equals to 1, y equals to 0, and z equals to 1. So we have solutions. But what the theorem says is that they are all trivial, in the sense that they always have at least one of the x, y, and z equal to 0. So this is a much harder statement than showing that there are no solutions, period. Okay? And so what does the field? So I gave you now this new language to speak about such problems. So this is a problem from number theory, but it turns out that it's very useful to think about it in another guise, so with another clothing. And that's what I'm gonna do in the following, in the last part of this slide. So what geometry tells us is that this polynomial corresponds to a variety, but more precisely to a plane projective curve that has some genus. So the genus is a geometric information. It's a geometric invariant. And the genus of this curve is something which, since it's plane, it's very simple to describe, and it's a function of its degree. So the genus of the curve is the degree minus 1 times the degree minus 2 divided by 2. And in this theorem, notice that we are concerned only with curves that have degree at least 3. The number n, which is the degree of this polynomial equation, is at least 3. So when we plug whole numbers that are at least 3 in this formula, we get that the genus is at least 1. And I chose to talk about this example, well, first of all, because I think that you all know, you all saw it at some point throughout your life, but also because it's a curve. And for curves, we have something very nice, which I'm going to describe in the next slide. So for curves, this very same geometric information that I wrote here, which is encoded in the genus, is telling us a lot about the whole number solutions of these polynomial equations, or the rational solutions of these polynomial equations. Okay, notice that I will not go into this, but of course that I could have stated the theorem with a Q instead of a Z there, right? I could be speaking about rational solutions. Clearly, every whole number solution is a rational solution, and vice versa. From a rational solution, you can produce a whole number solution by clearing my denominators. So it's also a theorem about rational points on this curve. And back to what I was saying, the geometry of this curve, which is encoded in the genus, and more generally for all, for all curves, the geometry tells a lot about the set of rational solutions, so of Q points. And that's encoded in this very nice slide. I think this slide has a lot of information. It's one of the richest one from this talk. And as you can see, in the first line, I'm dividing curves in three categories. So the curves of genus 0, curves of genus 1, and curves of genus larger than 1, strictly larger. So genus at least 2. And the genus, I gave you a formula for the case of plane curves, but maybe you like to see things geometrically, really. And in the fourth line of this, in the fourth line, you see that I am looking at these curves. When I look at them over C, over the complex, what I have is what we call a Riemann surface. And curves of genus 0, so before I go into each class, let me tell you that what the genus tells us is also a topological information about the surface. Namely, the genus counts the number of holes of the Riemann surface. So that's another way, if you want, to roughly define the genus of a plane, of a curve, And so now back to each case, let's have a look in detail at each one of these cases. So genus 0, the sphere, no holes. I'm always assuming in this slide that I have at least one solution, so at least one point over the rationals. And what's happening in genus 0 is that from that point, I can construct a map, which is, if you want, bijection from my Q points to P1 over that field. In the sense, here I have K, but it was supposed to be Q here. I'm sorry for that mistake. So I have this map that from one solution, from one point, produces a P1 of them, namely a line of points. So the set of solutions over Q, when I'm dealing with a curve of genus 0, as soon as I have one solution, I have an infinite set. So the geometry of these curves is telling me that I have a bunch of them as long as I have one. And you can see here in the one example that I plugged in, which is the one equation behind Pythagoras' theorem. And we know that we have an infinite set of Pythagorean triples. So this makes sense, right? So let's go on to the intermediary class, namely curves of genus 1. So curves of genus 1, as soon as they have one point, they are what we call elliptic curves. And elliptic curves, they're quite distinguished. First of all, because it was shown by Leonard. This was by, let me maybe give one example below. So this, as we spoke about, they are Riemann surfaces with one hole. So they look like this donut. I gave you one example here, which is the Fermat curve of degree 3. And the very nice thing, then now going back to the structure of the set of rational points, is that this set has a group structure. So over Q, we know this since the beginning, since the middle of the 18th century. This was actually shown much before we knew what an elliptic curve is and that we knew what a group is, actually, this fact. So by working with elliptic, by trying to generalize formulas like the one that gives us that, for instance, the log of a plus of a times b is the log of a plus the log of b, right? So these kind of formulas generalize and to show that the set of rational solutions, so of rational points in an elliptic curve, is actually a commutative group. But later than that, so already in the 20th century, Mordell showed that this is also finitely generated. So something great, because finitely generated commutative groups, they look very nicely. They look like what you see here in the second line, just below g equals 1. They have some finite part, which I denote by t, and some free part, which is z to the power r. And this number r can be 0, so this group of points can be finite, but r can also be bigger than 0. And in that case, I have an infinite set of solutions. And this is great. So this class stays in our mind as the classes for each everything can happen. I can have a finite set of solutions, but I can still have an infinite set of solutions. And moreover, since this is a plenary talk, I think I can say general facts that I assume not all of you know. One nice thing is that it's still an open problem to determine whether this R is bounded or not. So in the sense that the largest rank, so the largest R known over Q, is a record that has been standing since around 2000 something, 2008 or 9, by no one else, and this is 28, the record as of, so for the last more than 10 years, this has been standing as the record of the rank, of the highest rank of an elliptic curve. But this doesn't say that we don't have one of rank 30 or 100. We just don't know yet. And now we pass to the last class, genus bigger than 1. And for that class, the set of solutions is a finite set. And this has been shown. So first, Mordell proposed this as a conjecture, and Falting showed that in 1983. And in fact, he got the Fields Medal for showing this. So as you can see here in the little picture in green, these curves, well, when I have genus bigger than 1, there is at least 2. So I have at least 2 holes on my Riemann surface. And I give one example here. You start with the Fermat equation with any n bigger than 3, strictly larger. And what's happening here is that the geometry is so complicated, so the complexity of the surface does act in detriment of to the presence of rational points. So that's what's happening here. So in this table that I want you to keep in your head, in one end I have a lot of solutions as soon as I have one. In the middle, everything can happen. And in the last end, I have only a finite set of solutions. So it's a very nice and well divided classification. And for curves, the message to take home is that geometry determines the number theory of curves. So the Diophantine questions about curves. But not all polynomial equations give curves. If they did, everything would be simple. So many polynomial equations that, as a matter of fact, most of them give higher dimensional varieties. And this talk is going to be concerned with the next step, so which is that of surfaces. So when we pass to surfaces, we have a few guiding questions. So we are concerned, as I said, with the set of k points. So this set here. Okay, and the first question, if I want to study this set, which is the first very natural one, is do I have a point? So is this set an empty set, or is this set non-empty? Assume that it is an empty set. I want to know why. And for instance, I'm studying the set of whole number solutions or of rational. Okay, and if I reduce mod p, okay, which is something that we see in the first year, right? When we start university, I reduce mod p and I found no solution, then I certainly will not have solution for Q. If I look and over R, there is no solution, so there is no real solution. certainly there is no rational solution, right? But vice versa, say that I actually showed that there is solutions for the real numbers and that there are solutions mod p for all p's primes. Is it true that I then have a solution over the field of the rational numbers? And this is a very hard question, and varieties for which this holds are said to satisfy the Hasse principle, but this is not the theme of today's talk. But I wanted to tell you that this is a field that people work on. So that's why I made a little break here. But then we pass to the left side of my slides and look at the non-empty case. And then I want to know if this set is an infinite set. It's the same question that I would ask for a curve. Or I want to know if it's a finite set. So these questions up to that stage here make sense for curves. And but the next ones don't, because I can still have an infinite set of solutions, but there are two very different scenarios that can happen. So the first one is actually that all my solutions lie in one curve or in a finite number of them. So I can have all solutions concentrated in some curves. And in that case, why am I bothering to study surfaces? I can just study curves, right? But there's another scenario, is that my set of k points can be everywhere on my surface, in the sense that no curve captures them, or no finite set of my curves that lie in the surface capture them. And in that case, we say that this set, x of k, is Zariski dense. So it's dense for the Zariski topology. So the Zariski topology is the topology on an algebraic variety. So here we are dealing with a special case, which is surfaces, on which the closed sets, they are the proper subvarieties. So in the case of surfaces, my closed sets are points or curves. So if they are not concentrated in a curve, then they are dense for this topology. And that's one, I would say, one of the biggest questions when we are dealing with surfaces is to understand when this happens. So when is the set x of k points, so of solutions that lie in the field k, dense in the Zariski topology? So this is an arithmetic question. So it's a question of number theoretic flavor. And but the question that we really want to know for surfaces is, does the same that happened for curves, namely geometry determines arithmetic, still holds for like them for my surfaces? And if so, to which level? So what kind of statements could I get? Can I get a nice table like I showed you? So yes, we can we can have a nice table, but the table is not going to tell us as many plain and beautiful facts maybe as the first table told us. So let's have a look at the classification of surfaces. First, let me tell you that when we classified curves, I used the word genus. I chose to do so because that's the word that I do expect that most of you heard of at some point of your life. But I could have classified the curves according to the Kodaira dimension. So, and that's how it's a much more general invariant, which by means of general, I mean that I can define it for higher dimensional varieties. And that's precisely the invariant that we use to classify surfaces. But there is a good parallel. So I could have used this invariant. And in the classification of my curves, this invariant would appear in the following way. So I had the genus 0. You would have Kodaira dimension minus infinity. I have genus 1, the ones that lie in the middle would have Kodaira dimension 0. And I have genus bigger than 1, and these have Kodaira dimension 1 in the case of curves. But what I want for you to bring home about Kodaira dimension or about genus, right, in the case of curves, that I think that the drawings told you from the other slide, from the previous slide, is that, well, genus 0, so Kodaira dimension minus infinity for curves, corresponds then, in the language of human surfaces, to having a positive curvature. So in that class, I have no holomorphic one form, okay? When I go to genus 1, the ones that had Kodaira dimension 0, this corresponds to flat curvature. So, I have no curvature, right? So these curves, the ones that have genus 1, have precisely one holomorphic one form. And when I pass to genus at least 2, then they correspond to human surfaces of negative curvature. And then there is a lot of holomorphic one forms. But the Kodaira, so as I said, the Kodaira dimension is the way to speak about surfaces. So the classification that I present here is a geometric classification, is a birational classification, if you want. And as you can see here, I have the first class that would be in parallel to curves of genus 0. So the rational curves, I will have rational surfaces. So surfaces that have a lot to do with the plane. So this means that there is a birational map from P2 to this surface, or from this surface to P2, whatever you want for direction, or they are a product of any curve C by P1, by really the line, the projective line, my rational curve. So those are the surfaces of Kodaira dimension minus infinity. And now to the question, to the arithmetic question. So the geometry was Kodaira dimension. The arithmetic question is what's happening with the set of k points of solutions. Is this set a dense set in the Zariski topology? Is it not? And as a matter of fact, in the first class, we have both things happening depending on the surface that I look. So there are many surfaces that are rational surfaces, all these ones for which I will have Kodaira dimension minus infinity, and therefore, I have a dense set of k points. But I also have the ruled surfaces when the genus of my curve is bigger than 1, for which I have a non-dense set of k points. So for that class, we already see that everything can happen. Then I have the classes in the middle. The classes in the middle are the classes of Kodaira dimension 0 and Kodaira dimension 1. So this is the correct, maybe, a rough parallel to the curves of genus 1, the elliptic curves. And in this class, the first one, I have 4 subclasses, namely K3s and Hikis by elliptic, and the complex, and the tori. And I have many of them that are known to have a Zariski dense set of k points. And I have no example for which the set is not dense. Then I pass to the second class to the third class, where again, everything can happen. So these surfaces of Kodaira dimension 1, they are what we call they have a genus 1 fibration. So therefore this name here that you see, honest elliptic. And so they have a family of genus 1 curves that lie inside of them. More on that soon. Finally, the surfaces of Kodaira dimension 2, they are what we call surfaces of general type. So of course, that's where most of the surfaces will lie, and that's a zoo, therefore. So a lot of bizarre things happening, but we have no example for which the set of k points, so of solutions to the polynomials that define these surfaces, are Zariski dense, so dense in the Zariski topology. And we have many examples for which it is not a dense set. But I have prepared one more slide for you on which we go a little bit more in detail on this question of density of solutions over K. But before I go on, maybe let me tell you that, the message to take home here is, unfortunately, at that point, all we can say is that, well, the Kodaira the Kodaira dimension of the surface does not dictate the behavior of the solution. So the arithmetic of the surface. So this is not dominated by the Kodaira dimension. This doesn't mean that we cannot find maybe another invariant or another structure that dictates this behavior, so that will tell us precisely what is happening in the world of K solutions. But the next slide then summarizes the state of the art, and moreover tells you also what is not known yet. So in the first class, when we forget about ruled surfaces and focus on rational surfaces, so the ones that are birational to the plane, we have two minimal kinds of surfaces in these classes. So two birational classes that we have to study more, and they are the Peso surfaces or conic bundle surfaces. And sometimes they're both of them at the same time. And a lot is known for both of these classes. And in fact, we have had progress very recently in the past 5 to 10 years, but there are still things that we don't know. So there are still problems to be done and solved in this class. And this is the simplest class, okay? Coordinate dimension 0, there is a conjecture. So what we expect in the field here is that there is a finite extension of the field K over which the points become dense. So maybe the points are not dense over K, but there is a finite extension of it over which they become dense. And that concept is known as potential density. And this is known for many surfaces. I will come back to that fact soon in a slide when I talk about the main tool, okay? So now we pass to Coordinate dimension 1. As I told you, they always have a genus 1 fibration, and a little, maybe knowing a little more about this fibration can turn out to be very useful to know that the points are dense, but we need more information. So just having a genus 1 fibration is not enough. So just having these nice curves lying there is not enough, because it's not clear that these curves have points. And therefore, we have to study a little more to make sure that these genus 1 curves have points. As soon as they have points, we can play ball, because as soon as they have points, we have a family of genus 1 guys, and therefore I do expect to have a dense set. And here I'm speaking very roughly and as general as I can. Finally, we get to the last class, and Bombieri-Lang's conjecture, it tells us, it kind of explains to us, if this is true, and we do think it is, why in the previous table we had no examples for which the points are dense. And that's because we don't expect it to be true. So we do expect that for any finite extension of the field K, the solutions over this finite extension, in the case here I denote by K prime, are never dense. So we do expect for this class that the K points, so the solutions over K, they are all accumulated in a subvariety. And this conjecture is much more general, and we expect it for higher dimensional varieties as well. So it's not something just about surfaces. But now I gave you kind of a panorama of what we know about at least when it comes to Zariski density of the set of K points on surfaces, or of Q points. So we are looking, I do recall, for those who are not familiar, we are still studying solutions to polynomial equations. And these polynomials describe surfaces, so two-dimensional varieties. And I want to know if there are a lot of solutions that lie, in a certain sense, in the field of the rational numbers or not, okay? And I'm assuming here, when I'm speaking about density, that I have at least one to start speaking about density. And what I want to do from now on is to start to explain to you what kind of tools turn out to be very useful to prove results in that slide here. So everything, I will not say everything, but a lot that is done in that slide has been done. Well, it's far from all of it, but a good and very nice part, let me be real, has been done with the help of a specific tool. And I'm gonna explain to you what tool it is in the next slide. And they are elliptic fibrations. So as I told you, in the first slide of this talk, I want to use curves to understand surfaces. And that's what elliptic fibrations do. So I start with a surface. As I told you, I'm going to denote it by the letter X. And an elliptic fibration on the surface X is going to be a surjective morphism. So you have this map from my surface X to some curve B, such that a few things are verified. So first of all, almost all fibers. So I have fibers in American English and in British English. I'm sorry about that. So almost all fibers, they are smooth curves of genus 1. And this means that what is a fiber? So the fiber is an inverse image of a point that lies in B. So I take a point in B, a small b, and I look at what is lying above this point in the surface X. I'm going to show you with a nice picture very soon. And there are smooth curves of genus 1. Who are they? The curves that lie in the middle of the table of the curve classification. I also assume that there are singular fibers, so that some fibers are singular curves. So when we are describing our curve by a polynomial equation, say that I have a plane curve, this is really the same as saying that partial derivatives vanish all simultaneously. So they are singular fibers. So I have singular curves happening. And I also assume that there is a section. The assumption of a section is not always present for people that study these surfaces, but it's a very important one when you want to give statements about rational points, about solutions over the field of rational numbers. And this assumption implies, in particular, that the fibers are not only curves of genus 1, but that they have a point, and therefore they are elliptic curves. Okay, so a picture is worth more than 1,000 words, as you all know, right? And here, so in red, I have my fiber. So above a point, I have this elliptic, nice, smooth genus 1 curve. Then in blue, I have a singular fiber. I actually wanted to make a nodal curve. It was just, I couldn't do it, so I made this banana curve for you. But in green, I have a section. So a section is somehow a copy of B, but inside X, okay? And it's a curve that meets every fiber in precisely one point. So if you have a section over K, this means that you have a point over K in each one of these curves, okay? So a few nice examples of equations of surfaces that have these fibrations. Sorry, before we go on. So a few nice examples are, first of all, take a family of plane cubics. So, plane curves, okay? Here I didn't write projectively, so I don't have the Z happening. You can imagine, okay? You can make this homogeneous polynomial in X, Y, Z, and then I have the variable T denoting the parameter of this fibration. So you can think of P1 of T as being the curve B from the slide, okay? So this means I have a map from the surface whose equation you see here to the P1, to the P1 of T, so to the T line. And so you see this very clearly, right? Fix some T. For every value of T that you plug in, you have a genus 1 curve. You have a section. Actually, here you see clearly the section. It's something defined over K is the point at 0, 1, 0, right? Gives you a section. And when I plug, for instance, T equals 0, I have the cuspidal cubic, which is a singular cubic with a cusp. So I have precisely what I wanted, and this satisfies the previous definition from the other slide. But now I give you another example, a little less simple, but also clearly an elliptic fibration, which is the following. Now I'm giving a surface which is described by two polynomial equations. Again, so I have a surface which is described by the intersection then of the zero locus of these two polynomial equations. And as you see, the polynomials are not now in 2 or 3 variables, they are in 4 variables. It's x, y, z, and w. So every time I fix a t, I have homogeneous polynomials in 4 variables. So what I'm talking about in the language of the field is a complete intersection, okay, of quadrics in P3. And this is precisely a genus 1 curve for every value of t. So I have here, again, a map from the surface described by these 2 equations to the line P1 of t. So to the line over, with t as a parameter. But as I told you, this is a very useful tool to deal with problems in the field, both in geometry, but also in the, let's say, number theory related of surfaces. And that's what I'm going to discuss a little bit in the next slide. So first of all, why do we care about elliptic fibrations? And there is many reasons to care, and the ones that I'm going to list here are far from an extensive list that would really, it's far from a list that has all the reasons. It's not a comprehensive list, sorry. And the first one, it's a very useful tool to treat the question that I proposed here, namely to prove that the rational points are dense. So every time you have an elliptic fibration, and as soon as you manage to produce some kind of section that is non-torsion, maybe after you change the base or after some modifications you produce that, you can use this to prove that the set of k-points is Zariski dense. And I have used this successfully with Ronald van Lauk from Leiden about 10 years ago or a little less, to prove that the set of k-points are Zariski dense for certain Del Peso surfaces, so surfaces in the first class of Kodair dimension minus infinity. And Bogomolov and Schinkel have also used them, but to deal with the question of potential density. So density when you pass to a finite extension of the field of K3 surfaces. But they also have been used successfully very recently in about 2015 by Kolar and Mella to prove unirationality of conic bundles. And as I told you, remember I told you that the record rank standing at the moment is 28 for an elliptic curve over Q. And actually this was found, very surprisingly, if you want, for those who are not in the field, by using by looking not at one elliptic guy by itself, but at a family of elliptic curves. So at a surface, actually, as a matter of fact, he looked at a K3 surface and found as a fiber the curve that has rank 28. They're also useful to tackle just if you don't care about number theory and you don't want to solve solutions over Q or over the whole numbers, you want to care about what's happening with the curves as a more, let's say, general statement inside of your surfaces. And the Shioda-Tate formula relates a group of, that takes care of what's happening with the curves, or more generally, the divisors within my surface, which is called the Neron-Severi group, and it relates it with the Mordell-Weil group of my elliptic surface, which I didn't tell you what it is, but it's something that comes with an elliptic fibration with section. They have also very successfully been used many years ago, in the 90s, independently by these two people, to produce dense sphere packings. So everywhere you look, they can be really found and in a very useful way. And as a matter of fact, 3 of these densest packings still do hold as of today. So we have 3 different dimensions, which I don't recall now, and the densest packings are given by using lattice, which are related to surfaces that have an elliptic fibration. And finally, I have recently used them to produce some very nice, some good, which this good has a more, let's say, precise meaning, locally recoverable error correcting codes. okay? And this was together with Tony Verily and José Felipe Valor. So now I pass to the last part of this talk, and that's concerned with K3 surfaces. So I want to have a look at a specific class of surfaces, and the reason is going to become clear to you why. It's a multifolded reason. And so first I'm going to tell you what they are. So from the algebraic geometric viewpoint, so the definition that we normally give is that one here. So it's a surface, smooth projective surface that has trivial canonical bundle, and it's regular, okay? But if you are a differential geometry, the definition you might have encountered is that you have a nowhere vanishing holomorphic to form, and those are simply connected surfaces with this nowhere vanishing holomorphic to form. So being regular is a little less, I would say. But the nice thing that maybe you didn't encounter neither, and you don't work in neither of these fields, but still you might want to know what these surfaces are and what do they really represent within the classification of surfaces. And maybe this sentence here in more black, right, in the boldface, is telling you what you should maybe take home, namely that they are Calabi-Yau varieties of dimension 2. So Calabi-Yau varieties are one way to generalize elliptic curves, so the curve that lie in the middle of the classification. And I think maybe looking at a few definitions, so two examples, or maybe one example or so, is enough to get a feeling of what's happening here. As I told you, they are surfaces. I'm looking at more precisely, the ones that are defined by polynomial equations. This is not always true for the general K3s, but here we are, really focusing on them. And so I put two examples of algebraic K3s. And first of all, I have the quartics in P3, any smooth quartic surface in P3. So some surface defined by a homogeneous polynomial of degree 4 in 4 variables is a K3. A double sextic, which means that I have two copies of the plane of P2 that I glue, with a curve of degree 6 being the glue, okay? So this is represented by this polynomial equation here, which is not homogeneous at all, which is w squared equals a polynomial of degree 6, which is the one that I used to glue in the planes, these two planes, okay? But maybe you should keep the first example in your mind for this talk, because they have appeared before. Somehow this is a modification of the Fermat, right? I just added one term, the w here. But they look a lot like the Fermat, guys. But somehow some nice things happen for these surfaces. But before we go on, I reinforce my reason for speaking about K3s. And this is because I have a very broad, there's a lot of people from different fields here. And the reason to choose K3s is is the fact that they are everywhere, the ubiquity of K3 surfaces. So they appear from differential geometry, so they are known for a long time to be, they have this structure of a Kähler variety in physics, and more precisely in string theory and in mirror symmetry. They are used to study this. They do think that the universe has more dimensions than what we can see. And these dimensions, they are actually Calabi-Yau varieties, but Calabi-Yau varieties of dimension 6 or 5 are very complicated, and therefore they look at these toy models, which are K3 surfaces, so they cut them and they study K3s. Well, somehow, surprisingly, or maybe not, they appear in, with a, let's say, relation to group theory and to the Mathieu group, to the sporadic Mathieu group, M24. They were also related previously to M23 by, I think Mukai, who did say, that the symplectic, maps inside my K3, they kind of embed in an M23, in the sporadic Mathieu group M23, and somehow they have attached to them in a very actually nice way differential equations called Picard-Fuchs equations that describe how the period varies within families of K3s. They do have a very natural measure also, which is related to this nowhere vanishing holomorphic to form, is determined by it. And they have been recently studied in dynamical systems by people who care about positive topological maps with positive topological, entropy. I have a bug here. Let me see if I managed to, okay, went on. So now the question to conclude is I want to relate these two classes. So I want to relate these two definitions, namely K3 surfaces that I just defined to you, gave you, very nice, gave you two equations describing some K3s. And the question is whether they do have this nice structure of elliptic fibrations. And well, here I have a very bad news. If you just ask someone who studies moduli of K3 surfaces, they're going to tell you that they don't have an elliptic fibration, but actually many do, because the moduli space has a stratification given by the rank of some group, the group of the Néron-Severi group, and after a certain rank, we always have sections. So we always have the structure that I did define to you a couple of slides ago. But now I want to finish my talk very soon with with one nice K3, and that's the one that you saw before. And the second or the last line of the slide is also something you saw before. So this quartic surface here that we gave as an example of a K3 actually can be rewritten as a complete intersection of these two quadrics, of these two families, right, of quadrics in P3. And therefore, it has one elliptic fibration inside of it. As a matter of fact, I will tell you more about it very soon, because what happens for K3s, and the reason that I started to study them with more detail, is that they are very special. And they are the only class that might have more than one such structure happening inside of it in a non-trivial way. And so it's a natural, thing to wonder or to do, which is to classify all these structures, because you can have 50 such structures happening at once. And I wanted to conclude this talk by telling you that that's something that we do, and that I was not the first one to want to do that. So this is a very nice problem to work on. And since let's say 80-something, by Shioda, Nishiyama later in the 90s, many others, they worked in these classification problems of elliptic fibrations. And more recently, I worked with Garbagnacci, who is in Milano, in classifying elliptic fibrations on K3, but we proposed a new method to do so. And that's what I described in one of my last slides. I think I promised a last slide for a while now. We're getting there. And the main, it's a lot of words in one slide for going over time. But what I want you to take home here is that what we do to classify this genus 1 fibration, these nice fibrations inside the K3, is to take this harder, request to a simpler one. So we transform it to something much simpler by taking the quotient by some non-symplectic guy inside of my surface. And therefore we get some simpler surface, which is rational. And the reason I chose to show you this one slide with the method, or with the core of our work. So this work has been explored in 4 papers that we wrote so far, but this is really the last slide, which is why our method is so nice. It's because not only we could take a lot of things out of it. So we started with one work that we just wanted to get to know for one class, and then we saw that there was a lot to be done, but it has been used by other people. So this was a geometric problem, let me tell you, classify fibrations, nothing over number fields. But then very recently, last year, and in 2019 and 2020, Julian de Meyo used it to prove a very nice problem from number theory, or something that is really for K3 surfaces. So they have been really used recently, and that's why I wanted to call attention to this to you. So I'm going to finish here finally, and thank you for your time.
Thank you very much, Cecília. Let's see if you have some comments or questions in the YouTube chat.
Okay.
We'll wait for a few minutes.
People are shy.
Can you read this?
I cannot read anything actually, but I can open the YouTube. Let me try to.
What we can call to a surface with Cordero dimension 4, 5, etc.
Thank you.
What we can call to a surface with Cordero dimension 4, 5, etc. Okay. Mohammed Tahir.
Now I can read the question. Thank you very much. So thank you for having this question, because I realized I maybe didn't explain the definition of Kodaira dimension, and maybe if I should have done that, it would have been more clear. So the Kodaira dimension, let me maybe explain very briefly now. So there are many ways. So we are working with projective surfaces. So this means that they lie in some big projective space. And there are many ways of putting the surface in a Pn, in this projective space, which can be, maybe I put it in a P5 with one embedding, maybe another embedding is putting it into P6, and so on. But there is one specific way of putting it inside a Pn, which is the way that gives rise to the Kodaira dimension. And the Kodaira dimension then is precisely the dimension of this embedding, of this specific one. So this means that it can be at most 2, the dimension of the surface. So in case of curves, we can have at most Kodaira dimension 1, of surfaces 2. And when I say minus infinity, just to be clear, because it doesn't make any sense, this means that I cannot produce such a very nice way of putting the surface inside a Pn by using a specific divisor inside of my surface. So I can still do it, but with another divisor, not the divisor which is normally, I use it, which is the canonical divisor. So that's why I cannot have surfaces of Kodaira dimension 3, 4, 5, etc. Thank you for the question.
Let's see. Oh, another one.
Oh, no, I get a very hard question. I don't know how to answer this question. So are there some relationship with the geometrical equivalence of nilpotent groups? I want to say yes, but I fear I will say something stupid. So I'm sorry, I cannot give an intelligent answer to your question. Yeah, Adilson. Sorry about that. I'm sorry. I don't know, it's a space-time algebra. So I don't know if I can answer this question, but let me maybe answer something else, which is that K3 surfaces are really somehow mystical. In the sense that we know a lot about them, but they manifest themselves in so many fields. I wouldn't say mystical in the sense that we don't understand. On the contrary, I think a lot of people have been working on them, so we do understand a lot. But I find fantastic that is one of these things that you find everywhere through mathematics, and which is not a simple structure, right? Of course, we find groups. We find like simple things, but such a thing so special, right? And yet it manifests itself in relation to modular forms. It manifests itself with relations with dynamical systems. So in many ways, but that one, I don't know how we can relate to space-time algebra.
Let's see if there's another question. Well, I think we can thank you, Cecília. Oh,
thank you, Jacqueline. Very nice to see you here.
Yeah, it was really a nice talk, Cecília. Thank you very much.
Thank you, thank you, Mato.
Oh.
Thank you all for all this nice.
You have a lot of admirers here in Brazil.
I am very happy. I'm really happy to speak about the things that I really love. So it's great to be here. And I'm sorry that I didn't answer one or two of the questions.
Okay, thank you, Cecília. We are now going for a break. And at 4 o'clock, we start with the sections again.
Yeah, bye-bye.